Yeah, that's good. Glad to see that you all are happy. Tonight, I think what we'll get done is a review for your final exam. Don't forget that you need to be studying for and prepared for a final exam, which is scheduled for, I can find my calendar here, Monday the 20th. So that's this coming Monday. It'll be during normal class time. It will run later than usual. Normally, they schedule final exams for about twice the class period, but I don't think you'll need that much time. And we will do the exam then. Many of you need to do very well on the exam because you didn't do well on the first couple exams or you haven't been participating fully. And to avoid having to sit through this again with me, you might as well try to do as good as you can or to accomplish as much as you can on the exam. If we look at the course schedule here, the final exam itself counts for 30% of your grade. That's ABC, right? So you get 0 on this, you're down to a 70 already. And that assumes the others that you got, complete participation and homework. And we didn't really have any individual labs this semester, but they would count in here. And I'll look back and make sure if any can be counted that they get counted. And then the other 2 exams we had count 20% of your grade. I'm not sure whether it's 10 and 10 or 15 and 5. I'll have to look at the grades and see which one makes most sense. Or I might just take them based on the number of questions, make it look like a single exam. So don't second guess yourself. Just work as hard as you can to do as well as you can on the final exam. Without me having to go through them every single time we sit down, let me remind you that cheating is disallowed on the final exam. So if it's something you've been doing on the other exam, a couple of you have, you should not do that. Some of you did that with the homework. That's unfortunate because you don't learn as much that way. And I count homework as a basic did it run, was it working, as opposed to nitpicking every single line in the code, which I could do, but I just don't do. I was a little disappointed with some of you in the last homework assignment, the processing assignment, and that you changed the data you were going to work with, which is different than the specification I gave you when I assigned the homework. Use this, change the code file, and that's all you get to change. And some of you supplied all sorts of images and things like that, which you just can't do in real programming world. You have to follow the assignment. And so although you had something that looked like it was working with the wrong data and didn't work at all with just my data set. Some of you did very well on that, by the way, very well. I was very pleased with the code I saw. So we want to focus right now on winding down the class. This is the last night of lecture, and we'll do what we need to do. Are there any topics that you in particular can think about that you want to make sure we go over? I'll stick them on a notepad over here on my screen if there are. Robert?
A lot, the electrical engineering side of things, transistors, resistors, and when they're active, when they're
okay,
saturated.
Mostly transistor?
I'm a little hazy on all of the formulas, how to find the values.
All right, over here, that. Okay, I wrote down transistors and all the formulas. Anybody else have any other items that they're wanting to go over? Now, again, if you wrote down every word that I said during the semester, you're going to be in real trouble on the final because if I give you 100 questions and give you an hour to do it, you don't have time to go digging through the notes on every question. So you're going to want to make sure that you know the material. And that, of course, not asking other people what the answers are. I wouldn't expect to find a whole bunch of you in the same room taking the test together. Had that happened last semester. Of course, they got caught. Wouldn't expect you all to be on Discord chatting about what you're doing. I've seen some very strange things on Discord. And, you'll be doing it by yourself on your own to show what you know. If you can do that and you can prove yourself, you'll get a good grade and you'll move ahead. Mohammed?
Yes, Professor. Can we also go over 80 mega 328p? Just the basic concepts. I remember in previous class you just tested us on some quick question. Can we cover that one more time? I mean,
Okay, so 18 mega facts and figures?
Yeah.
Okay. Will do. Okay, what else? Now, I also realize that for some of these things, there's calculators online you could use. You could go search and say, I want to see an IEEE 754 calculator. Well, there'll be one. Here's one. You could fill in the numbers and it would tell you the answer. But don't do that. That's cheating. Okay, now you may find cheating to be just fine in your world, but in real life, it's not. And you'll get penalized in the big picture for that. For one thing, if I catch you, even if I don't tell you I caught you, you'll never get any recommendations or things out of me, which people often look for. Not that you'll have told somebody to come to me for a recommendation, but they'll know you were in my class and ask me about you. And if the only thing I can remember is, oh yeah, he was cheating, then I'm not going to have I won't tell them that, of course, but I won't have a very good report on you. Dante, do you have any questions you want to go over?
Yeah, could you just go over encoding and decoding the 1888 again?
Okay, the 8088?
Yeah, just encoding and decoding instructions.
Okay. We can. Okay, well, if nobody else has anything, we'll jump in. I'm going to cover other things as well, just some of them for review, some of them so you go, aha, yes, I remember we did talk about that. But maybe you haven't gone back and looked at the syllabus in a while and figured out how things are related to each other and why they're arranged as they are. Initially, the first night or two, we actually should have hit a lot of topics that you should have known already, but most likely didn't, because you're coming from the 101, 10, or 201 experience at Mercer, and sometimes these things are not as covered as highly as they would think. But things like number systems. Make sure that you can go, decimal to hex. You can go hex to binary. You can go binary to decimal. And conceptually, if somebody gave you something in base 8, you could go from base 8 to base 13. And we're not going to do any examples of that because we did plenty the first night of the process of doing those. But if you understand your number systems, it should be very straightforward. One of the biggest bugs I've seen people do in languages like Java is they'll build a, integer array, foo, and then they'll populate it. And they'll say, okay, I have a 10, I have 100, I have a 1, 2, 3, I have a 23. And then they go process the array and they get the wrong answer. For instance, they add the numbers up. Now, those of you that are Java gurus, stay silent for a second. And anybody else that wants to think about it for a second out loud, why would they get the wrong answer if they added up the members of that array? Nobody? Anybody that knows Java want to jump in and tell us why? Mohammed?
When you add them, it will, instead of adding 10, 100, and all those numbers, it will just line them up and just print out all numbers in a line.
Well, no, it will produce a sum. We'll get an answer. It's just the answer will be wrong. Sorry, God.
I think it's gonna take the 10, that's the first number, as 100 maybe when it's adding.
Well, let's us sit here and add this up as a column. 3 plus 3 is 6. 2 plus 2 plus 1 is 5. And 1 plus 1 is 2. This answer is wrong for the problem as presented. Now, I know some of you guys go around, signing your name and putting Java programmer at large. So what's going on here? Scott?
Full disclosure, I had to look this up, but leading zero literals like 0, 1, 0 are treated as base 8.
Exactly. This number is in base 8. This number is in base 8. So what's the real value of this number? Robert?
That would be 8.
And what is the value of this number?
19.
Notice how I left the leading zeros off of these. So in order for this to be fine, some nice person came through and lined everything up. But this would have given us a correct answer if that was an 8 and this was a 19 that we had intended to add. But if we'd really intended on adding, a 10 and a 2, 3, then we would have put a 10 here. And we'd have put a 2, 3 here without the leading zeros. Now they're decimal numbers. They're no longer base 8. Why did we have to know base 8? Well, it actually is used in places, and you can run across it and need to recognize that you have it. Robert just did a conversion. He noticed that this position, when it was in base 8, is 8 to the first. This would be 8 to the 0. 8 squared would be the next position. He just computed 8. Down here, he took 2 times 8, which is 16, plus 3, which is 19 in decimal. So he did a very good job of doing those conversions for us. And Scott, thanks for the full disclosure on that. I appreciate it. Okay, so we know things about number systems. Knowing that we have number systems and knowing how they're related, it was determined that we should know our powers of 2. And they kept coming back throughout the semester, and the people who hadn't memorized them became very obvious. I would ask, what's 2 to the 15th? And there would be this wall of silence with a little cricket in the background. And those powers of 2, to move quick enough, like knowing your alphabet when forming words, are necessary in order to be able to talk about computer science. In the digital world, we base it on base 2. And so we need to know our alphabet. We need to know how to convert from any power of 2. And we took several techniques. For example, we took 2 raised to the 3rd. What number is that? Well, that's a memorized number. And we know that to be memorized to be equal to 8. Let me just put it on the same line here. In decimal. We know that if we wrote that in hexadecimal, I can't get the equal key. Where'd my equal key go? There it is. 8. In binary, it's equal to what value? And we learned our nibbles from 0 to 15. So the nibble for 8 is, Scott?
1000.
Right, and that's base 2. We just tell you that without the subscript, because I can't type subscripts. So all this is in decimal. That's in hex, should have subscript 16. This should have a subscript 2. Remember that the subscript describing the base is always in decimal. Otherwise, if I said, what's that number, and I didn't tell you the base, you have no idea what it is. If I tell you the base, or I imply that it's base 10, you would tell me it's a 10. If I tell you it's base 8, you tell me it's an 8. If it's base 16, it's a 16. So depending upon the base, 10 is always the name of the base. Now it became handy when using the binary numbers to be able to look at various types of encodings we could use on them. One of the encodings that we very briefly touched on but have used later in the semester was something called binary coded decimal. Oh, let's say we wanted to code some numbers in binary coded decimal. And somebody said, encode the number 1, 2, 3, 4 in binary coded decimal. And then they said, how many bytes will it take? First question was, how many bytes? And we'll ask another question if necessary. So how do we encode that into binary coded decimal? I've seen this question recently without the same number, but somewhere nearby us. Who wants to take a shot at that? How would we encode that in binary coded decimal? Scott?
The idea is to use a nibble to encode each decimal digit.
Right. So if I had this, what would the first nibble be?
Going from left to right, it's going to be 0001 and 0010, 0011, 0100.
That's right. So we've got byte and a byte. The nibbles are actually the digits. If you're asked to encode this in that, we just make sure that any of these digits are decimal, meaning they don't exceed the number 9. And we saw some algorithmic stuff that showed what to do if we increase these. You might remember double dabble and some of those things. So encoding numbers are important. Why in the heck why is it important to be able to encode numbers or facts? Mohammed, why would it be important for me to be able to write a coded something?
Is it because computer can only read numbers and it's just important for us to know?
Right,
how
a
to do
computer
it?
can only deal with numbers, and the numbers need to be in base 2, which means each bit of the number will be a 0 or 1. And so if we want to represent something that's meaningful, we have to have a unique bit pattern which will represent that. Let's say that I had the song 76 Trombones. What's the minimum number of bits I need in binary in order to encode the number 76? So each trombone could have a unique encoding. You guys are making me worry. I don't want to see all of you again next semester. Although I like to see a big bunch of you back. I think if you're not going to do the work this time, next time you will. Basu?
Is it 7? 7 number?
Is it 7? 7 bits. 2 to the 7th is equal to what?
Oh. 2 to the 7th, 128.
Okay. So would 6 bits be able to do it? 2 to the 6th?
That's 64.
And 64 isn't big enough to contain 76 unique items. So we would need a minimum of 7 bits. What's the maximum number of bits we need to encode the 76 trombones? Somebody else answer. And Basu, what you have a lot of feedback when you're on your microphone. We hear everything we say after we say it. What's the maximum number of bits I can encode 76 trombones in? Numar?
Is it 128?
So 128 was the minimum.
Oh, you said maximum.
Or what's the maximum? Robert?
I mean, you could technically use as many as you want, but you only need 7.
Right, so the minimum is 128. The maximum is infinite. I can use as many bits as I want to encode those 76 things. It doesn't mean I have to have an exact fit. You know, if somebody said to you, will your foot fit in a size 13 shoe? For almost everybody in the room, yeah, it'll fit. Should you buy it? Probably not. What size fits you? Oh, you're a 9 or a 10.5. Whatever the size is, get that. It'll be the best fit. Will you fit in a 6? No. So same thing here. We can determine what the minimum number of bits that are necessary, and that's a very important thing to be able to do. Where the open-ended maximum of it. We could, one simple case that proves it could be a big number is, let's say that each one, I'm going to have 76 digits there. That's the first trombone. There's the second one. There's the third one. So I could encode, and the last one would be all zeros, ending with that 76 positions out. But I also could have used 77, 78, 79, 1,000. I could use as many bits as I want to encode it. But optimally and practically, I can't store it in less than 7. Will 7 bits always be the best to use? Is there any reason why I might want to use 10 bits instead of 7 bits? What do you think, Robert?
You may want to encode a parity bit. You may have other information you want to store beyond just identifying it.
Okay. That's a very reasonable thing. So there could be other ways we could start. One of the things that strikes you immediately is I'm storing it in 7 bits. If the minimum object I can pick up is an 8-bit object, is there any advantage to storing it in 8 bits? Maybe I can arrange it in such a way when I go from one to the other, I don't have a repeated bit. This is a real problem. Well, let's just count in all numbers. I'll do it, repeat it again. If this is my sequence of numbers, as I go from here to here, we have 1 bit change. As I go from here to here, we have 2 bits change. Now the problem is, what if the bits change in the wrong order, meaning this guy changes before this guy does? We get a 0, 1 longer than we needed it. Should have been a 1, 0 sooner. Is it conceivable we could accidentally get a 1-1 while we're ready to get a 1-0? We'd have to look at it and see. Now, we fixed this problem using an encoding. What was the encoding we used? Dante?
Do you mean gray code?
Yep, we use gray coding. In which case we arrange the numbers so between any two, there'll only be a single bit flip. We also talked about an encoding which is very similar to this one, which we use to maintain the current state of a CPU. What encoding did we use there? What type of counter did we use to implement that encoding? I'll give you a clue. It's what everybody says when they see me walk down the street. They go, man, that's one hot dude. So one hot. They don't actually say that, by the way, unless I'm on fire. So one hot encoding. One hot encoding is kept in our machine inside a certain type of counter. What do we call those counters? Scott?
A ring counter?
A ring counter. A ring counter is simply a counter that uses a one hot encoding and shifts the 1 bit to various positions depending on when it's clocked. Now, we don't have any problem there with things being misinterpreted because we're always changing 2 states, the one that was 0 and the one that is, and we know if 2 ones are on, we're in the process of changing state. So it's a safe encoding. We encode our T states there for CPUs. That's why we studied it the very first night of class, was to be prepared for that. We spent some time talking about the encoding of ASCII. ASCII. How many bits is ASCII encoded into? Sargon?
7 bits.
When it's transmitted using RS-232, how many bits do we use? Now, the very last night of class, last time we were talking about ASCII characters, and we were using RS-232 to send characters from our program running on the Windows machine to the Arduino so that it could process them as Morse code. So you must surely know how many bits we used if you've been studying that code. When we send ours, we're sending 1 start bit. We said 8 data bits, meaning we're padding it. We're sending 0 parity bits and 2 stop bits. That's what we did when we went from the serial monitor to the 18 mega. But we could have encoded other lengths. What are some of the other lengths we could have encoded? Well, we could have done this. One start bit, the 7 data bits we have, plus one parity, and we could use either odd, even, mark, base, or none parity. None parity normally would not be sent as a bit. Instead, you'd send 8 bits, but we should account for it. And we could have sent 1 or 2 stop bits. This is what we chose, and if you were looking through the code to find it, let me grab a piece of code here. I don't think y'all are having as much fun as I am. You never sound like it. Sending 8 data bits, 2 stop bits, which we could verify by looking up what these bits mean. There's always a start bit. And since we didn't mention parity, there are no parity bits sent. We could look and we'd see that there was no parity. So let's actually go to the use of doing that. Let's look this register up. Where do we find that? Because you'll certainly be asked to do this on the exam. Some of you, by the way, are probably going to get some programming assignments in addition to your normal questions. Not everybody gets the same questions. So where am I going to go look that up? Dante, where should I go?
We're going to go to our AT mega data sheet. And
I
then,
should go there. Hang on a second here. Okay, where am I going next?
and then we're going to go to the register summary. It's page 621.
Okay, well, let's find it over here. So I'm going to go down and find the USART, which is here, USART 0, section 20. Open that up. Where do I go inside here?
And then we're going to I was going to the sorry, I was going to the register summary, so I didn't go through this way.
Okay, go to the registers. The last thing is always in each section is a description of all the registers. We need UCSR 0C. UCSR 0A, B, C. So it must be this page. So in my book, it's around page 202. 203 in that neighborhood. And we're going to look at that guy. I think it's this one I can push. And here are the bits that we need to set. We're setting USB S0. Which will be the bit right here. And we're setting the SZ, the size. This is, starting the size parameter. So 0 and 1 are here. So we're enabling the size, which says we're using 2 stop bits. We left the parity bits as 0, so parity is disabled. We also, up in this set the first selection bits to 0, which means it is an asynchronous USART. This would be if we're using a clock, and this would be if we're using another type of communications with this port. So we set it to 0 because we wanted an asynchronous USART. We disabled for parity with 2 stop bits, and we wanted our character to be, we need 1s in the 0 and 1 field, which would be here and here, which means we picked 8 bits of data. We could have had parity also. We could have had 9 bits, right? But we didn't. We chose to be 1 start bit. We don't choose that. That just happens for free. number of data bits we want to send, which are our 7 plus one extra bit that we just let be 0. Our parity bit, none, we're not using it, and 2 stop bits because that's what we said we wanted. That gives us longer time between each character for the hardware to recognize it. Anybody have any question about what we just configured there? Okay, then say somebody said that they wanted to know what that did. We can look at the comment, but let's look it up in the bits. What are we doing right here? Now actually do it. Don't just sit there waiting for somebody else to answer. Scott, where do I look to find this register?
Look in the data sheet for UCS R0C.
Well, we're going to be using, oh, C, yeah, you're right. No, I said, what's this guy? This is the guy we're checking. So it's B.
Oh, oops.
Okay, I imagine B is right in front of C. And we were just past him. So here he comes. We're setting the bit TXEN0, TX RXEN0, TXEN0, and RXCIE0. So here they are. We're setting RXCIE, that's this guy. We're not setting him. We're not setting him. We are setting both of these and none of the rest. So if we set RXCIE something, we're going to say cause an interrupt when a character is received. We have to read about it a little because it says it's automatically cleared under certain circumstances. Because if you remember in our code, we don't specifically clear it. We just simply read a character and move on. The other two are RXEN and TXEN, which will be down here, which basically say enable the ability to receive characters and enable the ability to transmit characters. Now, not all our programs need both of those. And if we were going to actually write one as a production program, we'd come back and then fix this. This is set for the general case, and we'd have a specific case. For example, in the last program we wrote, we never wrote a character back, so we could turn transmit off. We also could get rid of any code for the RC send function or USART send. We wouldn't need this. One more thing. What does this do? That would be a great test question, by the way. Dante, what do you think that would do?
So it says it doubles the USART transmission speed.
Okay.
So so it lowers reduces the baud rate divider from 16 to 18, doubling the transfer rate for asynchronous communication.
Right. Remember somewhere up here in our code, we said we want to operate at 9600, meaning our speed itself isn't going to change, but then we set a number in a register which causes us with the normal counter to get to 9600 character or bits per second. And what we've done is if we use that value turned on, this number is only half as big as it needs to be because we're going to be able to count to a lower number and still get to this within the same period of time. Now, I always have trouble finding this. I think I searched for baud, B-A-U-D, and then here's examples of, go there, scroll down this table until you find a clock of 16 megahertz, which is right here. The frequency is being run is 16 megahertz. Find the baud rate you want, and then find out what number you have to store in these registers over here, which would be 103, unless that bit is set, in which case we have to store a number twice as big, because remember, we're counting half as slow. I'm sorry, we're counting twice as fast in order to burn up that amount in the same time. They have the same percentage of error. We just chose this one, not particular reason. It's convenient because this guy fits in a single byte. This guy wouldn't. Even more so, this guy wouldn't, but that guy would. So it might be easier to encode him in a byte and then encode this variable to a 0. But you can look those things up if somebody asks you to configure this thing for a particular baud rate or particular receiver transmitter speeds. Okay, we can come back to this. This is a diversion because we were talking about ASCII on night 1 and talking about that exact piece of code there on the last night of class. Okay. Where is this? We also talked about when we were taking numbers in binary, we talked about how we would combine them using arithmetic. And we said we're going to add those two nibbles together. In this case, we get no carries anyway. We get a value like that. Now, we did not specify in advance whether these numbers are signed or unsigned numbers. If we say they're unsigned, we use all the bits and treat everything as a positive number. So this would be a 1, this would be a 10, this would be an 11 in decimal. But if they're negative numbers, we're going to encode them with a 1 at the beginning. Now, part of doing that means that we should be able to determine what a number is. If it begins with a 1 by flipping all the bits back to what they need to be in order to show the positive version of the number. So if we took 1010 and we decided to take the 2's complement of that, we would have to follow an algorithm. And we have 2 of the algorithms. One of them is flip all the bits and add 1. And the other was something I called the Coakley method, because one of the students in the past named Eric Coakley devised that method and has allowed students to have 2 ways of resolving the answer. Let's first of all flip all the bits and add 1. Let's use the Coakley method, which says find the last 1 and make everything after it stay the same. Flip everything in front of it. This number is equal to what in decimal? This is a memorized nibble, so you should know. Patricia?
6.
And what would this be then?
10. Oh, negative, sorry, negative 6.
Negative 6, that's right. Okay, so if you're looking at one you don't know what it is, you can find its positive version and put minus whatever the name of this is. Now this is important because if I'm sitting with a number that looks like this, and you say expand that to 8 bits, I'm going to do that. If I have a number that looks like this, and you say expand it to 8 bits, I could do this, or I could do that, depending on whether the numbers are being interpreted as signed or unsigned numbers. And we have to know how it's going to be treated. We saw in our instruction set for the AT Mega an instruction which did arithmetic shift right, which was different than a logical shift right. In what way? Robert?
The logical shift right loses any data that falls out the other end, whereas the arithmetic shift right, I believe, uses the carry bit to store that information.
No, that would be a rotate.
Oh, sorry.
Easiest way to think about it is look at this number, extend it out like this in a register. And again, we'll just so we have for completeness, we'll do this. This one is produced with a logical shift right. This one is produced with an arithmetic shift right. This one, it was produced with either one. They give you the same answer. When you have a negative number and you do an arithmetic shift, you drag in the sign bit. And it does it by just duplicating the top bit and passing it on. And which, of course, same thing going on here when you use arithmetic, but it's a 0. That's kind of important. And Robert also mentioned there was a rotate instruction. And where am I getting this stuff? Am I just making this up? Let's go down to the bottom here. In the instruction summary, I have to remember where they are all the time. It's not there. It must be up in the first set. I've lost it. Where is it? Did I spell the instruction wrong? Oh, yeah. There they are. Logical shift left, logical shift right, and we go a little further down. Here's the arithmetic shift right. There is no arithmetic shift left because there's no point. The sign bits on the left, you'd just be pushing them out. And then the ones he was referring to are these two here. Rotate to the left and rotate to the right. They're 9-bit rotates with the 9th bit being the carry. It's in exactly the same shifts and things that are on, for example, the SAP2. So you'd have to pay attention to the architecture of the machine you're using. We talked about fixed point binary. For example, if I put a radix point inside of a number that's written in binary, that point stays fixed relative to other numbers I might write. So if I were going to combine that with, something that looked like that, the points line up. Now, I probably wouldn't write the number this way. Instead, I would write it as a nibble here and as a nibble here, since I have at least one bit in the nibble. But the idea here is we can encode a number, and we'll assume all positive numbers here, as being, what is this value right here? What is it in decimal? Again, this is a nibble. What's the decimal value, Robert?
That would be a 8, 10, 11.
point, now we're using a decimal point as opposed to a radix point. Fractionally, what does that equal to?
So that's 1/2 plus 1/4 plus 1/8 plus 1/16. Which I guess is. I'm gonna have to think about that for a second.
Well, it's 1 and you have 15 of them. So it's 15/16. So 11 and 15/16. Now I could write it like this because it implies the point, or I could grab my grocery store calculator, which I haven't grabbed in quite a while. Let me grab it. See what screen it even comes up on here. And I could take 15 divided by 16. And so this number here is 0.9375. So in fixed point, this is not unlike the way we encode IEEE 754 floating point. What's the primary difference between us expressing that number and how we would express it in a floating point number? Robert?
For floating point, we have, I don't remember all the terms, but the mantissa, you have to encode how far the decimal point is away from the beginning of the number. So there's a number of different things that have to go into floating point.
Okay. One of the things that we want to look at with the floating point is what's the sign of this number? Now, I told you it was positive, so we'll just stick some zeros out here to indicate that to ourselves. So when we would encode that, we have a positive number. We also normalize the number if possible, meaning we don't have to move it 126 places. We can normalize it. In our case, we're going to move it 1, 2, 3 positions. The decimal point is going to wind up right there. Okay, so I'm going to get rid of the dot there, change it to this. And remember that I just made this number smaller, so I'm going to have to multiply it back by 3 places. So I'm going to write a number here now, which is 3 bigger than 127. So we have our 127 biased exponent increased by the number of decimal places we're going to need to put back into it to get back to our original number. So what is 127 plus 3? Let's write 127 down. Actually make it all be one number there so it's easier to look at. And I'll put a separation between it and the sign. We know that's 127 because if it had been that, what number would it have been? Count your places. 1, 2, 4, 8, 16, 32, 64, 128. So it's 1 less than 132, and we said that anytime you wanted to be 1 less than something, and it's all zeros now, you can just simply turn off the bit that was on and put all ones to the right of it. So this is 127, to which we have to add the number 3. I can already see I'm going to get a 0 carry the 1, 0 or 1 carry the 1. It's going to be a little harder to do than I want it to be just in simple math. So why don't I do the following? Why don't I simply, instead of using 127, use the 128 I had and add 2 to it instead of 3. And then use that number as my exponent. Well, let's just stick a 0 in front of that for the sign and we'll continue on. Now remember with IEEE floating point, we know we're normalized, so it always has a 1 to the left of the decimal point. So we're simply going to take everything that's left, stick it to the right of the decimal point. then break things into sets of 4. Oops. What did I do there? What am I doing? I don't think I have a redo key on this. So so this got combined with that. 4 here, 4 there, and 4 more. And we need 4 more digits once we get it next, because this is going to be a 4. It'll be a 1. It'll be a 3. This will be an F. Then we need 0, 0, 0, 0 to get our full 32 bits. And we would have encoded this then into IEEE 754. Since on this exam, you're going to have to show your work on a problem like that, you're going to make sure you can do it. And this is like, for example, I showed you where a calculator was. Don't use the calculator because you're going to have to show your work, and it doesn't show your work for you. And who knows if I got it right? I might have made a math mistake. I was doing some pretty crazy stuff with my cut key there. We'll have to see. But that's the general plan. Notice how it was related to how we do it in fixed point binary. So as long as we can encode our number in fixed point binary, we're good. We'll be able to do this conversion. It's easy. Sign is 0 or 1, depending on whether it's positive or negative. The exponent is biased by 127, meaning that you start at 127. If you had to move the exponent to the left, you're going to add numbers to it. You had to move to the right, you're going to move it the other direction. You're going to take numbers away from it. Sometimes it's easier to add a smaller number to 128 than it is to add a bigger number to 127. If I were subtracting, this would have been easier because I could just turn those into zeros. Now, there were some special cases inside IEEE. We actually should put sign there. If the sign is 0, the exponent is 0, and the mantissa is 0, what's the value of the number we have? Scott?
Positive 0.
Okay, well, I've got you. What's that equal to?
Negative 0.
Okay. Now, it turns out that those numbers, even though they're physically written in different bits, if you say, are they equal? They are equal. So you can compare them and get equality out of them. They're not different, even though they would be encoded differently. What do we have here? Scott?
Positive infinity.
What do we have here? Scott, you can answer that one also.
Negative infinity.
Do they compare equal?
No.
Yeah, they shouldn't. It doesn't make any sense for them to compare equal. 0, it does. Infinity is as far each direction as you could go, so they shouldn't be equal. But, well, one of you tell me what not a number is. How do we encode not a number? Which is abbreviated NaN. Lowercase a usually. Dante?
If the I don't think the sign matters. If the sign is 0, the exponent is all 1s, and the mantissa is not all zeros, then it's not a number.
Yeah, good. I did it with my cut and paste. I'm good at this cut and paste stuff sometimes. So it's not all zeros there, right?
Yeah, not all zeros, yeah.
Then it's not a number. And this can be either 0 or 1. Doesn't matter. So if I wrote a number down, well, let me do it the other way. And so forth. Are they equal? Robert?
They're both not a number. Doesn't necessarily mean they're equal, though.
How about these two guys?
Again, I believe the only thing we can determine is that they're not a number.
That's exactly right. They can't be compared. So just the act of comparing them is wrong. So they're not the same. Now we have one other set of cases here, which is basically the same as if we copy a 0 line here, but not here. Make this be, just say 0. And this could be either positive or negative as well. I won't list them separately. Among the terms that these are called is denormalized. They have some other terms for them. But what that means is, you remember a while ago when we encoded a number that looked like this and we threw away the one on the left of the dot? When we get here, we're no longer encoding an exponent. It's always assumed to be 2 to the minus 126th. And we have to encode the entire number, including whatever's to the left of the decimal point. So basically what we're doing is we're moving the decimal in front of all the numbers implied, and then we encode all the digits. And that's the basic rules for IEEE 754. So we knew those better than we thought we did. We talked extensively about Unicode and encoding. I'm not going to review it now because we really reviewed that heavily before the last exam, but expect some problems. And again, don't go finding a calculator somewhere and using it. That's considered cheating, and you're not supposed to cheat on exams. You know, it says something about you, not your result. You know, who cares if I can go out, you know, and steal something and it's mine now? Big deal. If I earned it, that's worth something. So Unicode, you need to remember all of the forms and all the different ways they can be encoded. And in arithmetic, pay particular attention to the use of full adders versus half adders. We were using that on the ATmega 328 very clearly, where we had a pair of registers to be added together. So we're going to add, you know, our 28 and 29. Well, I'll put 29 at the first. And our 30 with our 31. Well, I'll do that again the same way. We're going to add those together as 16-bit numbers, and we're going to use 8-bit instructions to do so. We have a 16-bit, so we're not going to use it. We're going to use the 8-bit. I have to add the lower parts together in case they generate a carry to be used with the upper parts. So let's say I did a load immediate into register. Well, let's not even put values. We'll assume they have values in them already. What two instructions would I need to use in order to properly add these together? Robert?
First you would use ADD, and then you would use ADC.
What am I going to do with the add? What registers?
You're going to add the low register, both
Which in our case is 28
and R30,
and R30.
and then
And then the ADC.
R29 and R31.
What if I had done this? Is there a difference?
Certainly. I can't remember exactly what it was, but wasn't there something about making sure you add the low bit first? Oh, wait, that is the low bit. I'm not entirely sure.
Anybody else want to take a shot at it? Well, what's the result of running both those instructions? What'll be different when those two instructions are done? Because they both produce the same answer.
Where it's stored.
Yeah, just where the answer winds up. In one case, we wipe out 28 and 29. In the other case, we wipe out 30 and 31. So it depends on what you needed, where you wanted the answer to be when you were done. This is a register pair. What's its name on the ATmega? Basu?
Register Y.
Yep, you're right. What would this one be?
That's gonna be G.
Yeah, it's register Z or Z, depending on where you're from. Okay, excellent. Let's do a little circuit work now. Take a break from some of this computer stuff. Let's start out with some of our more simple things that we know how to do. Oops, I don't want to do that. And I'm going to make this an LED. Got a couple lightning bolts. It's pretty bright. We have a 9-volt battery, an LED, and we need to go to the store to buy a resistor. Tell me what we need to do. Who wants to walk me through this? How about somebody that hasn't spoken yet tonight? Hey, Bessie, what's the first thing I need to assume?
So you need to subtract the voltage that gonna be take off by the bulb 2.1.
Okay, since I didn't tell you, the LED has a 2.1 volt drop across it, if there's enough current to turn it on. So if I looked in the circuit right here, we'll draw a little ground thing. I would measure 0 volts. If I looked here, I would measure 0 volts. If I look here, I want to find 2.1 volts. If I look here, I'm going to see 9 volts. So how did I get from 9 volts down to 2.1 volts?
So so we need to drop the 6.9 volt on the resistor.
Okay. Now, is current flowing in this circuit clockwise or counterclockwise? Second?
Clockwise.
Okay, so it's going this way. So we need to know what the current is in order to pick the resistor, or we need to pick a resistor and find out the current. Do we have any design requirements for these? Patricia?
For the current, we assume that it's between 15 or 25, so we use 20 milliamp.
Okay, so we can say that the current for design purposes is 20 milliamps. Be very careful on the exam. If it asks for 2 digits, significant digits, make sure you round it to 2 significant digits and then give it not only 2 digits, but you give it in the form of engineering notation, which means it's not 0.02 amps. I want to see 20 milliamps. A couple of you missed questions on the last exams because you didn't pay attention to that. Some of you also gave me 3 digits. When it says 2 digits, that's pretty straightforward. So now we have this. Whose law do we get to apply to this? Is this the Thevenin equivalent law?
Use the Ohm's law.
Ohm's law. What is Ohm's law?
V is equal to IR.
V is equal to I R. We know V, which is 6.9 volts. We know what the current is, which is going to be 0.20. I'm sorry, 0.020 amps. When I'm working the problem, I can use it in its own form, right? In amp form, because this is volts, amps, and resistance. And then we have the unknown in ohms. So to solve this, I need to get R off of both sides. So divide this by R. It goes away. Divide this by R. I get the answer, right? Well, you could, but probably a better way would be don't swing R around to the other side. Swing this value. So divide this side by the 0.020 amps, which will get rid of the amps, and then divide this by 0.020 amps. So what is 6.9 divided by 0.020? Minotti?
345.
Okay, let me do it up here also, just so we've got a second thing people can see. 6.9 divided by 0.020. Is that what you got, 345?
Yeah. Yep.
Okay, can we go to the store and buy a 345 ohm resistor? The answer is we can, just not to the store we're going to. Okay, instead, we're going to assume it's a standard value. 345 is not going to be standard because first place it's multiple, it's 3 digits. But we should be able to go to our resistor standard chart here. Find something close to 345. What's the closest thing we've got? Patricia, which one?
330 ohms and 5%.
Okay, well, we've got 360. 360 is the same distance away from it, right?
Yeah.
345 plus 15 would be this. 345 minus 15 would be this. So when you come up with a case like that where it's evenly divided, figure out which one of these is also in the 10% table, which is 330. So she's correct. We're going to make a 330 ohm resistor. So how much current is actually flowing? Where'd my window go? So if instead of this being, what did we say, 335, 345? Instead of that, this resistor has to be 330 ohms. Since this drop is fixed, we need to see what value this is actually going to be. So instead of 20 milliamps, how much do we actually have flowing through there? Well, if it's 330 ohms, let's build a little table here. And it's 10%. What's the smallest value this can be? Mohammed?
Smallest value.
Take 10% away from 330.
That will be 297.
297. Right? 33 less than 330 would be 297. 10% less. We could add 33 to this to get the highest value resistance it could have. Let's see, what would that be?
The highest value gonna be like 363.
Yeah. So now we need to take the voltage and divide by each of those. So 6.9 divided by 297 is equal to 23 milliamps. On the other hand, if it was 363, 6.9 divided by 363 equals 19 milliamps. We have to make sure this number is between 15 and 25 milliamps. Make sure this number is between 15 and 25 milliamps. So this is an okay value. We just didn't figure out what the wattage is yet. So we need to do this equation again using the power formula. So 6.9 divided by 297 gives us the current, which then you multiply it back times the voltage again. You get the wattage using the power law or the rule for watts. We get 160 milliwatts. Be careful there that you would bring it to two significant digits, which is safely less than a quarter watt, which would be 250 milliwatts, but too big for 128, which is an eighth of a thing. So our resistor will be a 330 5 or 10%, we'll say 10%. Quarter watt resistor. What color would it be? What do the color bands say on it? Hermal?
Would it be orange, orange, brown, silver?
Orange, orange, brown, silver, yes. Silver means 10%. Wattage we can't read on the resistor, we just have to look at the size of it or the packaging to know it's the right size. If I put this all together, it would work. If I got the LED in backwards, it wouldn't work because current can only flow one way through the LED. It has to be in the direction current is flowing for it to light up. Anybody need to see any piece of that problem again? Because this is also part of the transistor problem. Okay. Well, while we're here, let's talk about some of the situations that a transistor can get itself into. We have a basic circuit that we've been using. As I recall, that's the one we've been using in here. The goal being to light up the LED without us be giving you any other data about this particular problem. What do we already know that I could overrule with a statement, but if I don't, we have some values for them. Patricia, what do I know?
You know the value of the LED is 2.1, and if there's no given value, we assume that the drop across the transmitter is 0 volts.
Okay, 2.1 volts here. And if I don't give you another value, meaning we're in saturation, full saturation, we can compute with 0 volts there. What else do we know? Samir?
The current is running counterclockwise.
On both sides?
The right side.
Yeah. Current's going this way on this side. It's going this way on that side. Bessie, what else do we know?
I think we know the value for the beta. If not given, it's 100.
Right. So beta is equal to 100 if you haven't been told otherwise. What else do we know? We know a lot here and haven't given you any values yet. Scott?
Absent any other information, we can assume that the transistor will drop 0.7 volts from the base to emitter if it's saturated.
Okay. What else do we know? You guys didn't know you knew all this, did you? Patricia, what else?
The current in the right-hand side is equal to 20 milliamps.
Right. This has to be, to follow our rule of lighting an LED, we're going to plan for 20 milliamps. What else do we know? Robert?
Going back into the power source, we would see 0 volts.
Yeah, down here at the bottom, we have ground. What else do we know? Robert, do you have another thing? Or are you just hanging your hand from the bus strap? Scott?
We can use a rule of thumb to figure out what current we need to saturate the transistor.
Okay, let's do that.
Okay, so
What number am I going to divide by what?
I'm going to take the collector current,
0.02.
0.02, divide by
Divided.
beta of 100. And our rule of
And?
thumb is to multiply that by 2.
Which gives us?
Gives us 400 microamps, which is our
That's fine.
base current.
Right, that's what we're going to plan for. You didn't know you knew all that stuff, and I haven't given you any data about the circuit yet. What haven't I given you that you might need to know to pick the resistor values? Patricia?
The value of the batteries, the VB
Yeah.
and VCC.
So VCC over here, we don't know a value for. Let's make it be equal to 10 volts. VBB over here is equal to what? Well, that's up to me to give you some value, right? You can't deduce it from this. I could give you anything I want over here. Let's make it be 5 volts. Now, do we know enough to finish solving the problem now? Which is basically what resistors do I need to buy? Well, let me ask you two questions that help in the calculation. What value is right here in terms of voltage? Samir?
Is it 7.9?
Now, if this were not 0, this point would be matter, because if this was not 0, you'd have to take the difference between 7.9 and 0, or 7.9 and this value, to see what the resistor drop is. I'm going to write the 0 here so we remember to put a value there if that changes. The other number we know is right here. What voltage is right there? Mazu?
It's 0.7.
And
After
what's the value? And what's the value right here?
over there is 5.
Okay, so 5 minus 0.7 gives us the drop across this resistor, which is
Right.
how much?
4.7. Oh, 4.3. Sorry.
4.3 volts.
Right.
This is going to be the same as this, 7.9, unless this value is different, in which case then it'll be reduced by that. So this is going to have a drop of 7.9. Okay, go ahead and calculate your resistor values and let's see how you do. Don't worry about picking a real one, just calculate the computed value. Give me a green circle when you have the values figured out. I'm calculating it should take you about 4.5 seconds to figure each one out. Okay, well, you should have a value by now. I didn't see any green circles popping up there. We got 7.4 volts dropping across 20 milliamps. Or that's 7.9. 7.9 divided by 0.02. So 395 ohm. Over here we have 4.3 divided by 400 microamps. It's 10,750. And you, of course, would trim this guy to a near value, 390 or 400. So do either one of those exist in the chart? Which one's there, Patricia?
390.
Okay, so we'll pick this guy to be a 390 ohm then. And this guy, is there something near 10 or 11K? Where is it? Well, 10 and 11 are both here. Now, is the number we had closer to 10 or closer to 11? It's closer to 11. So in this case, let's go for the 11. We just have to be a 5% resistor. So we'll actually buy an 11K ohm resistor. Now, I'm not going to redo the power calculations, use 10% or 5% more, 5% less for this guy, 10% more, 10% less for this guy. Use the current, figure out what the wattage is, make sure it doesn't, burn the chip up. So pick one that's big enough. And then also make sure that the current flowing over here is close to 20 at its highest and lowest values, which it will be if you followed the rules. Anybody have any questions about this before we make it more complicated? Basu?
How do we got 400 milliamp over here? I had
400 microamp.
right.
We took this current, this was Scott's suggestion, take this current, divide it by beta, which is 100, which would give you 200 micro. Double it because in order to get this in saturation, we want to guarantee enough current to force this as close to zero as we can get it. And so that came from that calculation. And we did that before we even knew voltages because it's not necessary to know the voltages.
Thank you.
Mm-hmm. Okay, things to watch out for. Watch out for this battery being put in backwards. Watch out for this LED being put in backwards. Watch out for that battery being put in backwards. Watch out for the transistor being flipped so that the arrow is on top. In almost, well, I guess every one of those cases I mentioned there where we'll not have sufficient current to turn on the LED because we can't make it, we'll go backwards to the LED. We'll just be an avalanche if we do. Another thing to look out for, if we don't have 0.7 volts here, if it's given that we have something like 0.3 volts, you don't know what to do about that problem. Unless it's 0.7, you can't calculate whether or not the light's on or not. On the other side, make sure this number is between 0 and 0.7 volts in order to make the LED be turned on at the correct current. If it's bigger than 0.7 volts, the LED might still be turned on, but the transistor will not be in saturation, meaning it's generating a lot more heat. So I can push this, value quite a bit higher, and the LED will still come on. And by picking a small enough resistor, I can cause the current to be 20 milliamps. But the transistor will not be in saturation. It'll be in the active region. And any small change over here to the base circuit will cause this light to change its brightness. So when we're forward biased on base collector and in the collector base, we're in saturation. In order for that to happen, the value between the collector and the emitter has to be below 0.7 volts. If this is the same as the power supply, the transistor's turned off and you get no flow anyway. What if I gave you the current circuit and I told you the value of the battery is 2.1 volts? Will we have the light turned on? The answer is no. We need the 2.1 to light it up, and we need a little bit to drop across this. And if it's exactly 2.1 and this is exactly 2.1, there'll be nothing left to drop here. And so it would be the same as having, the thing shorted out. Same thing over here. If I don't give you a value that's bigger than 0.7 volts, this can't reach 0.7 volts here and leave something to drop across the resistor. So those are all cases you'd want to look out for, if the teacher's messing with you. What would be different if you had been told beta is actually 75? What would change? Robert, what would change?
The 400 microamps would no longer be accurate because we use.
What would I calculate?
Well, we use beta in that calculation.
Let's use it. What would we do?
So that's one of the things that I'm not 100% on.
Okay,
yet.
well that's what we're trying to make sure everybody understands. We need to take the current we want, divide it by beta. We want 0.02 divided by 75. That would put us exactly in saturation. So we're going to multiply that times 2. And we're going to come up now with a value which would give us the current over here that we'll have flowing. So instead of 400 microamps, what's this value going to be?
Looks like 533 microamps.
Well, it's -4 here. Is that what you want, 533?
Or
Well, we would use 533. If somebody were to take and ask you what that number was, though, you'd say 530. When you're doing the calculation, you can maintain all of this stuff. But when you actually are pushed and ask what the value is, then you use, if it asks you to. Sometimes, for example, with time, they want the literal time. They don't want you to round it off. But in this case, let's assume this was the value, 533 microamps. That means we're going to need a different value resistor, but that's going to be the only thing that changes. So we have smaller amplification factor. And that's going to mean that when I take my value here, it's going to be harder to get it to be a big number. Okay, any more questions about this? None? Okay. Well, let us leave transistors a world then. Okay, where's our syllabus? We've done all of that. We do need to think again about combinational and Boolean algebra for just a second. The main thing we've been seeing lately is we had some rules that we talked about early on as electrical things that turned out to be great programming devices. One was so if I have an arbitrary binary number and I want to guarantee that this bit right here is turned on, what's the most appropriate Boolean operator to use to make that happen? Robert?
Or.
So what I would do is create a mask. It has a 1 in that position. And I would simply OR it against what's currently there. So in 18 mega code, if I had loaded register 16 with a 3.5, and then I did an OR immediate register 16 with a 0 hex 04, which is this guy turned into hex. Under the hood, I just took my 3, 5, my 0, 4, and I ORed them together. That means that guarantees those two will be on. This one will be on. And so the one I was interested in is truly on. Let's assume for a second that this number had been a 3-1. So I have a 3, 1. I OR it with this. When I'm done, I have a 3, 5. But we've guaranteed that that bit was turned on. Now, quite often when using registers, this is an operation you might have to deal with. For example, make up some arbitrary register. If I load from it, and the register's name is, I don't know, Baboom. And I want to have that bit turned on, I can do an OR against register 16 of the bit I'm interested in. And so in this case, let's say it is going to be the same one we were using there, 04, to get that to occur. But we have been typically coding that slightly differently. One of the things we've been doing is we've been creating or defining a word, call it whammo. We've been giving it a number. Give it a 2. And then when we write our statement, we've been doing an OR immediate into R16 of whammo, I'm sorry, 1 shifted over whammo number of times. Which equals what? What does this actually equal? What's 1 shifted to the left? Here's the number 1. Shifted to the left 2 places. If I shifted it 1 place, it would be 0 places, it would be right where it is. There's 1 place. There's 2 places. What's that number? 04. So by using, instead of this, using this, we've accomplished the same thing we did in the original problem back here. Assuming we picked up from Baboom the number 31, we ORed with it a bit we wanted to turn on, we'll wind up in that register having that bit turned on, ready to store it back. We just picked it up. The typical next thing we would do would be to, do a store into Baboom of register 16 after we've updated it. Everybody clear on what we just did there? Because we're using that all sorts of places in our code. We also Robert, what method do we use for that? What Boolean operator?
I'm sorry, I missed what you had typed.
Guarantee that a bit is turned off.
Oh, you could AND it with 0.
Right, we end it with a 0. So what that says is, using the same code down here, if we, instead of wanting to guarantee that bit's on, wanted to guarantee that it's off, what we'd have to do is put a 0 in that position. So that would be an FB. And that would change this to an AND immediate. We could do the same thing here with an AND immediate, but instead of ORing it with this thing, we want to use this style of notation. So when we're using the AND, it's still okay to identify the bit we want using this method. I remember if we have multiple bits, we can just simply OR them together in a row here. I'll use it, do what you'd be used to looking at. Where'd my vertical bar go? I've lost it somewhere in packing. There it is. I don't have keycap on that key. And so we could attach to this, you know, a 1 of some other bit, blammo. When we're done with all of this, or for example, just this, we'll take just this 1. What we can do is we can invert it using the tilde. Same thing here. We could invert, and then I want to put another set of parentheses around all of that, which basically gives us back this thing, but with the 0 where the 1 used to be. So we can use an OR to make sure something is turned on. In this case, we can't because I've just inverted it. And we can use an AND in order to turn off a bit. The other operator that we want to keep as being very useful is, in general, how do we toggle? Not using the atmega particularly, but using a logic gate. How do we cause bits to toggle? Scott?
Not.
Well, I want to do individual bits inside of a byte. So I have this, and I want to make that bit and that bit toggle. I don't know what they are. I'll just call them X's. But I want to make them toggle. Leave the others alone. Using a Boolean operator, how could I do that? Sargon?
XOR?
Yeah, we're using exclusive OR, right. So think about the table for an exclusive OR. What happens when they're both 0? Nothing. What happens when one of them's a 1? So if we think about the bit that we're testing against as being a 1, and this is the bit we're testing, it inverts because of the 1. If we leave that bit a 0, the output follows the second bit. So if I take an exclusive OR that says leave those alone, toggle that one, leave those alone, toggle that one, and leave that guy alone, everywhere we have a 0 in one of them, it'll be exactly what it used to be. So let's pretend like for a moment this guy is a 0 and this guy is a 1. First guy, we use the bottom row of their control, says stay the same, stay the same. Toggle, so the 0 becomes a 1. Stay the same, stay the same, stay the same. Toggle, so the 1 becomes a 0. Stay the same. Then we'll have been able to toggle. If we do it again, they'll toggle back to what they used to be. So that's one of the uses that we would use an exclusive OR for. And what is it called inside the ATmega data set or instruction set? Robert?
EOR.
EOR, right. Looks like a bad spelling of the word ear. Okay, let's see what else we have here. Do we need to do any examples of Karnaugh maps? Bessu?
Oh, I'm sorry.
How about, I'm not going to do any Quinn McCluskeys. They're too much fun. Okay. 47K home. How much time? Time questions, remember, we keep the decimal points unless they become ridiculous, like repeating numbers or something. So work that problem real quick. Give me a green circle when you have an answer. This is one worth working, because you'll see it again. I might even give you these same numbers. I don't remember. Did I put the curve on the first page? I don't remember if I did or not. I did not. Let me see if I have one. No, I don't have one, but we can still talk about it anyway. What's step one? What do we have to calculate? Second?
Would we use the formula tau is equal to RC and then calculate?
Tau is equal to R times C. R is in ohms, C is in microfarads, or I'm sorry, in farads. So let's write those numbers down that way, first of all. What's our resistance in ohms? Second?
47,000.
Yeah. And what's our capacitance in farads?
0.0001.
Okay, well, that would be the micros. We said 10, right? So it'd be that for micro. So we can take and do that calculation. Where's my calculator? I know I have it here somewhere. I saw it a second ago. So we can say 47,000 times 0.00001 equals that. So is that 0.4 seconds? Is that how long it's going to take to discharge? Samir?
You're going to use two significant digits, so it would be 47 milliseconds.
Well, if this was in milliseconds, it'd be 470 milliseconds because there's a zero. We need in sets of three. Patricia?
Don't you need to multiply it first to like?
Absolutely. What do I multiply it times?
To 5 to completely distribute.
Yeah, 5 times whatever our answer was from that. 5 times tau. That's called the RC constant. And we're going to multiply it times tau. So we can go times 5 here. And so that's in seconds. Because it's time, we're going to leave it alone. We're going to express it in milli or micro or for whole seconds or whatever we need to, but we're not going to get rid of the extra digits. So how would I write my answer for this one? Robert?
2.35 S.
Correct. Now, let's assume I hit all the right buttons. I might have calculated something wrong, but if I did, you'll figure it out. So that's how we would do that calculation. Make sure you can do that. Also, I wish I had that somewhere. Let me see. See, they give me a chart in here. Oh, why don't they do that? Oh, I didn't mean to do that. There we go. Oh, here's an even better one. I gave you one of these. Okay, somewhere in your handouts. I just don't have my handouts with me. Somewhere we've got a chart that looks like this. So a question might be, how long does it take to charge it to 86%? So how would we solve that problem differently? Scott?
Multiply the time constant by 2 instead of 5.
Right. Here's 86%. It sits right on the 2 line. So you'd simply multiply it times 2. Some of these you'd have to kind of eyeball to see that they're close. But if you were doing that, there'd probably be a multiple choice question. He gave you an answer that was in the ballpark. But just remember, it's not always times 5. The number you first get is simply the number that's going to get you to 63%. Now, I don't know if there's a discharge on this one also. Probably not. But it's the opposite of that. And it's the amount of discharge. So you would have discharged in one cycle, one tall, 39%. I'm sorry, not 39. One is here, 63%. So it would be a number that made the curve go down like this. And you have that handout somewhere. I just simply don't have it. Okay. These, you got more handouts than you need to know what to do with there. They should be easy to look up. Architecture. Anything I need to answer about the SAP one? Okay, you got that guy. How about the SAP 2? Robert?
Could we just do a brief flyover of all 3 of them, which features exist in 1, 2, and 3? Because I'm betting there's going to be a trick question where he asks us for a feature of the 3 in the 2.
Well, you might. If we take the SAP 1, the most obvious things it's missing are basically the idea of going to someplace. Okay. Or instruction set. Not much you can do. Can't write to memory. Anybody else think of any of the things I brought up at the time that were downsides? You know, kind of using it as a comparison is a little hard, but yeah, Robert?
No stacks or pointers.
Okay, we can use those as and some of this other stuff is probably supported by these, and so that's probably why they're not there. Always 6 t-states, even if you're doing nothing except for the halt instruction, which remember stops halfway through T3. Okay, that's the SAP 3 or SAP 1. It'd be awful if that was the 3. SAP 2, pretty good, but missing. What's this one missing? Mohammed?
It's missing no. It has no pointers.
It doesn't really have the concept of pointers. Okay.
It has no carry
else?
flag.
No what?
No carry.
No carry.
And no nested.
Which of
call.
course, you might mention he didn't have either. We can add it to the list. Okay, what else? Samir?
It doesn't have LDA and STA.
Well, no, it does. It has load and store. Well, this has no stack. I'm going to put here kind of does. In the fact that it only has a 1-level return, so we can support call and can support return, but it doesn't really have the same notion as a full stack. Up here, we also, I might have written it down in here somewhere, but the go-to kind of refers to it as sequential execution only. You can't branch. Let's see, what else are you thinking of?
It doesn't has the nested call.
Say that again.
Nested call.
I'm not understanding.
No nested call. Like we can go like nested the call thing.
Oh, repeated calls. We got that with the lack of a stack.
Oh, okay.
Yeah, you can't nest calls because if without a stack, you'd wind up unable to return. You have a good point. Okay, let's just put it aside for a second. Let's talk about the SAP 3. Instead of features it's missing, what does it have that the other ones don't have? Robert, what do you think? Anybody want to help him out? Scott?
We do have pointers.
Okay, we've got pointers in here. What else?
We've got a carry flag.
Carry, and it's a bunch of flags. Okay.
And we've got a full stack we can use.
Yeah, we can use stack. So now we can suddenly do calls. Non-sequential execution was given to us earlier. That was allowed back here, right? On the good side, can go to. So it's not sequential execution only. And this is more of same. And then finally, well, let's just say we're talking about the 8085, which is the extension to the SAP3. What did we add here? Primarily. Lisu?
Interrupt.
Yeah, interrupt processing. And some extra system instructions and things like that. But in general, that's about the main types of things. As long as you know the individual architecture and you could separate these apart, you'll probably be good on answering any questions that I can think of that I probably would ask you. Somebody said earlier they wanted to talk a little bit about the 8088 and talk about encoding and decoding and instruction. I don't think we have time to do both, but let's take an encode one. Let's move to DI. Let's encode that instruction. This is a hex number. Let's review real quick. What's the opcode for the typical move? Dante?
The opcode for the move is 100010, and then we have DWMM reg r/m.
Okay. So we know the first part of our instruction is going to start out. Is the register we're encoding, is that the destination or the source of our data? Dante, what is it?
The register we're encoding is the source.
Is on the right or the left?
Sorry, it's on the left.
Okay, so from the right to the left means that's the destination. And we code a destination as a what? Bazu?
1.
Okay, are we moving 8 bits or 16 bits, Mohammed?
We are moving 16 bit in this case.
Right, it's the size of the register, which is 16 bits. Okay, what mode are we using? What mode is this? It's one of the memory modes. It has an 8-bit displacement. So how do we code that? Dante?
We code that as a 01.
Okay, now we need to code DI as a register. Dante, you again.
That is 111.
And then we have to go to the mode table where there's 8 bits of displacement. We got to find BX plus D8. What's that coded as? Mazu?
101.
101?
Right.
Hey, let's break that up into its nibbles. There's 4, there's 4, there's 4, and there's 4. Okay. You can write that out in hex, which is 8B, 7D, but we're not done. What's left? Mohammed, what do we need to do?
Professor, isn't it 111 for just memory field encoding?
Which one?
The R/M, isn't it 111?
I don't know. He told me one was a 1. Which one is it?
I think it's 111 because BX plus 8 is 111.
Okay. Well, no, BX plus D8 is 111. Might be. I don't have the sheet. I'm doing this from memory. So that's an F on the end now instead. So what else do we have left to do with that? Robert?
We've told it that we need displacement, but we haven't told it what we're displacing it by.
Okay.
So we would need to encode the CD in there.
Okay, that's the instruction. Of course, you could work that backwards if you had to get back to an instruction. What is the addressing mode we're using? Drum roll. No, drum roll. I need my synthesizer program. Who kept my synthesizer program away from me? I was playing poker the other night, and I think somebody stole my synthesizer. So what is the addressing mode we're using? Scott?
Base relative direct.
That's exactly right. Okay, so I think we got that. We're coming up against end of class time. If you have all the review you need, you certainly are welcome to leave. You also, if you want to stick around for a few minutes, I want to go over the memory model for the AT Mega again. Somebody asked for some AT Mega facts, and just to make sure that if they needed to see that, we've done it. But you're free to leave now, and we'll see you Monday night. Make sure you're on time for the exam and that you're all well studied. You can pretty much have any notes or anything you want with you. You just can't use old copies of material that I've given to other classes or calculators or people, things like that. I mean, you know the rules. You also, if you know you're cheating, don't do it. Anybody have any last minute questions before we're done? Otherwise, the test is all we have left. And if you do want to stick around for a few minutes, I'll spend 5 or 10 minutes and go over the AT Mega register address thing. Some of you already have that written down so many times you don't need another copy. Okay, those of you that want to go, let's go so that I can get started with that with the other people.
All right, Professor. Thank you so much.
Bye-bye.